In mathematics and computing, the method of complements is a technique used to subtract one number from another using only addition of positive numbers. This method was commonly used in mechanical calculators and is still used in modern computers. The nines complement of a number is formed by replacing each digit with 9 minus that digit. To subtract of decimal number y from another number x, two methods may be used. In the first method, the nines complement of x is added to y. Then the nines complement of the result obtained is formed to produce the desired result. In the second method, the nines complement of y is added to x. If the result is positive, a leading digit, 1, appears and is an end around carry and brought to the least significant place and added. Discarding or carrying around the initial 1 is especially convenient on calculators or computers that use a fixed number of digits. There is nowhere else for it to go, so it is otherwise simply lost during the calculation. The nines complement plus 1 is known as the tens complement. The method of complements can be extended to other number bases. In particular, it is used on most digital computers to perform subtraction, represent negative numbers in base 2 or binary arithmetic in test, underflow and overflow in calculation. Numeric complements. The radix complement of an n-digit number y in radix b is, by definition, the radix complement is most easily obtained by adding 1 to the diminished radix complement, which is, since is the digit repeated n times. The diminished radix complement of a number is found by complementing each digit with respect to. The subtraction of y from x may be performed as follows. Adding the diminished radix complement of x to y results in the value or, which is the diminished radix complement of, except for possible padding digits. The diminished radix complement of this is the value. Alternatively, adding the radix complement of y to x results in the value or, assuming yx, the result will always be greater or equal to, and dropping the initial 1 is the same as subtracting, making the result or just the desired result. In the decimal numbering system, the radix complement is called the tens complement and the diminished radix complement the nines complement. In binary, the radix complement is called the twos complement and the diminished radix complement the ones complement. The naming of complements in other bases is similar. Some people, notably Donald Knuth, recommend using the placement of the apostrophe to distinguish between the radix complement and the diminished radix complement. In this usage, the fours complement refers to the radix complement of a number in base 4, while fours complement is the diminished radix complement of a number in base 5. However, the distinction is not important where the radix is apparent, and the subtle difference in apostrophe placement is not common practice. Most writers use ones and nines complement, and many style manuals leave out the apostrophe, recommending ones and nines complement. Decimal example. The nines complement of a decimal digit is the number that must be added to it to produce 9, the complement of 3 is 6, the complement of 7 is 2, and so on. See table. To form the nines complement of a larger number, each digit is replaced by its nines complement. Consider the following subtraction problem. 873 to 218. The proper use of nines complement requires no ambiguity in the sign of a written number. Ones complement is the analogous system for binary and always has a signed bit to tell if the encoded number is positive or not. In decimal, this rule is a little different, since the most significant place has 10 possible states instead of only 2. If the most significant digit of the number is less than 5, then the number is positive. The number 0 is not positive or negative, and the above rule says that the representation for 0 doesn't begin with 0, which is not entirely true. Nines complement, again in analogy with ones complement for binary, has two representations of 0. 0 can be written as is, with only 0s as digits, or where all the digits are 9s. 9, 9.9, 99, and even 999.999. All represent 0. This is why negating a number by subtracting all of its digits from 9s makes sense, because 0 is represented by the 9s. Negative numbers have the appearance of subtracting from infinity. The significance of the rule about the most significant digit can be seen if one simply writes down a number with a leading digit that is not less than 5, such as 83. The rule says that 83 must represent a negative number. When one does the 9th complement of 83, it is 99 to 83, 16. The result, 16, is a smaller representation than 83. It would not make sense if 16 represented the negative of 83. In other words, 16 equals is confusing if 16 represents a negative number. The leading digit of 16 is only a1, so the rule again contradicts with this. 83 equals is a much more reasonable conclusion. What, then, does positive 83 look like in 9's complement? To avoid the leading digit conundrum, a 0 is simply added on the left. 083 is positive 83. Negating 083 provides more evidence. 999083, 916,916 is very different from 16, the negation of 83. 916 represents, or negative 83, but 16 is just positive 16. First method again, 873 has too large of a leading digit to be positive, but it is supposed to be positive, so a leading 0 is needed. We compute the 9th complement of the minuend, 0873. Add that to the subtrahend, 218. 218 is positive, so it has a 0 in the same place as 0873 did. 0873, 0218 becomes 9126 plus 0218, 9344 because of the leading digit of 9. This answer is clearly negative, so its 9th complement needs to be calculated. 9344, 0655. Note that the 0 can only be removed from 0655 if it is written in the traditional sign and magnitude notation, where the most significant digit rule is irrelevant. Second method, we compute the 9th complement of 0218, which is 9781. Because 0218 is 4 digits long, this is the same as subtracting 0218 from 9999. The 0 in front of 218 is not necessary to show that 218 is positive, but rather to keep track of the fourth place due to 0873 needing the 0 to avoid it being interpreted as, instead. Next, the sum of x and the 9th complement of y is taken. 0873 plus 9781, 10654, because 9's complement in decimal is analogous to 1's complement in binary. The leading 1 is an end-around carry and must be moved to the least significant place and added to arrive at the correct result. 0654 plus 1, 0655. The 0 that remains in the front correctly indicates that the answer is positive and not. Magnitude of numbers. In the following example, the result of the subtraction has fewer digits than x. 123410, 123401. Using the first method, the sum of the 9th complement of x and y is 876,589 plus 123,401, 999,990. The 9th complement of 999,990 is 00009. Removing the leading zeros gives 09, the desired result. Writing 9 would again just stand for 0. If the subtrahend, y, has fewer digits than the minuend, x, leading zeros must be added in the second method. These zeros become leading 9s when the complement is taken. For example, 48032, 391 can be rewritten 48032, 00391. Replacing 00391 with its 9's complement produces the sum 48,032 plus 99,608, 147,640. Doing the end-around carry with the leading one gives the right answer. 47,640 plus 1, 47,641. Binary example. The method of complements is especially useful in binary since the 1's complement is very easily obtained by inverting each bit, and adding 1 to get the 2's complement can be done by simulating a carry into the least significant bit. For example, 011000000101110 becomes the sum 011001000 plus 11,101,001 plus 101,001,110. Dropping the initial 1 gives the answer 0100111. Negative number representations. The method of complements normally assumes that the operands are positive and that yx logical constraints given that adding and subtracting arbitrary integers is normally done by comparing signs, adding the two or subtracting the smaller from the larger, and giving the result the correct sign. Let's see what happens if x less than y. In that case, there will not be a 1 digit to cross out after the addition since will be less than. For example, 185 to 329 complementing y and adding gives 185 plus 670 plus 1, 856. This appears to be the wrong answer. The expected answer is minus 144. But it isn't as far off as it seems. 856 happens to be the 10's complement of 144, so 856 represents minus 144. This can be addressed in 3 ways. Ignore the issue. This is reasonable if a person is operating a calculating device that doesn't support negative numbers, since comparing the two operands before the calculation so they can be entered in the proper order, and verifying that the result is reasonable, is easy for humans to do. Represent negative numbers as radix complements of their positive counterparts. Numbers less than are considered positive, the rest are considered negative. This works best for even radices since the sign can be determined by looking at the first digit. For example, numbers in 10's complement notation are positive if the first digit is 0, 1, 2, 3, or 4, and negative if 5, 6, 7, 8, or 9. And it works very well in binary since the first bit can be considered a sign bit. The number is positive if the sign bit is 0 and negative if it is 1. Indeed, 2's complement is used in most modern computers to represent signed numbers. Complement the result if there is no carry out of the most significant digit. This is easier to implement with digital circuits than comparing and swapping the operands. But since taking the radix complement requires adding 1, it is difficult to do directly. Fortunately, a trick can be used to get around this addition. Instead of always setting a carry into the least significant digit when subtracting, the carry out of the most significant digit is used as the carry input into the least significant digit. So if yx, the carry from the most significant digit that would normally be ignored, is added, producing the correct result. And if not, the 1 is not added and the result is 1 less than the radix complement of the answer, or the diminished radix complement, which does not require an addition to obtain. This method is used by computers that use sign and magnitude to represent signed numbers. Practical uses. The method of complements was used in many mechanical calculators as an alternative to running the gears backwards. For example, Pascal's calculator had 2 sets of result digits, a black set displaying the normal result and a red set displaying the 9's complement of this. A horizontal slat was used to cover up one of these sets, exposing the other. To subtract, the red digits were exposed and set to 0. Then the 9's complement of the minuend was entered. On some machine this could be done by dialing in the minuend using inner wheels of complements. In displaying that data in the complement window, the operator could see the 9's complement of the 9's complement of the minuend. That is the minuend. The slat was then moved to expose the black digits and the subtrahend was added by dialing it in. Finally, the operator had to move the slat again to read the correct answer. The comptometer had 9's complement digits printed in smaller type along with the normal digits on each key. To subtract, the operator was expected to mentally subtract 1 from the subtrahend and enter the result using the smaller digits. Since subtracting 1 before complementing is equivalent to adding 1 afterwards, the operator would thus effectively add the tens complement of the subtrahend. The operator also needed to hold down the subtraction cutoff tab corresponding to the leftmost digit of the answer. This tab prevented the carry from being propagated past it, the comptometer's method of dropping the initial 1 from the result. The Curti calculator used the method of complements for subtraction, and managed to hide this from the user. Numbers were entered using digit input slides along the side of the device. The number on each slide was added to a result counter by a gearing mechanism which engaged cams on a rotating echelon drum. The drum was turned by use of a crank on the top of the instrument. The number of cams encountered by each digit as the crank turned was determined by the value of that digit. For example, if a slide is set to its 6th position, a row of 6 cams would be encountered around the drum corresponding to that position. For subtraction, the drum was shifted slightly before it was turned, which moved a different row of cams into position. This alternate row contained the 9's complement of the digits. Thus, the row of 6 cams that had been in position for addition now had a row with 3 cams. The shifted drum also engaged Y extra cam which added 1 to the result. The always present tens complement overflow 1, which carried out beyond the most significant digit of the results register was, in effect, discarded. In computers, use of the method of complements is ubiquitous in digital computers, regardless of the representation used for signed numbers. However, the circuitry required depends on the representation. If 2's complement representation is used, subtraction requires only inverting the bits of the subtrahend and setting a carry into the rightmost bit. Using 1's complement representation requires inverting the bits of the subtrahend and connecting the carry out of the most significant bit to the carry in of the least significant bit. Using sign magnitude representation requires only complementing the sign bit of the subtrahend and adding. But the addition-subtraction logic needs to compare the sign bits, complement one of the inputs if they are different, implement an end-around carry, and complement the result if there was no carry from the most significant bit. Manual uses the method of complements was used to correct errors when accounting books were written by hand. To remove an entry from a column of numbers, the accountant could add a new entry with the tens complement of the number to subtract. A bar was added over the digits of this entry to denote its special status. It was then possible to add a whole column of figures to obtain the corrected result. Complementing the sum is handy for cashiers making change for a purchase from currency in a single denomination of 1 raised to an integer power of the currency's base. For decimal currencies that would be 10, 100, 1000, etc., e.g., a $10 bill. In grade school education. In grade schools, students are sometimes taught the method of complements as a shortcut useful in mental arithmetic. Subtraction is done by adding the tens complement of the subtrahend, which is the 9's complement plus 1. The result of this addition used when it is clear that the difference will be positive. Otherwise, the tens complement of the addition's result is used with it marked as negative. The same technique works for subtracting on an adding machine.